I'm Andrea Woody. I am the chair of the Department of Philosophy, and I'd like to welcome everyone here tonight. Let me begin by thanking a few people that helped make this event possible. The first is Kate Golden, who is the development coordinator for the Department of Philosophy, and she coordinates all the events that come out of the department. The second is my colleague, Ben Feinzig, who is an assistant professor in the department and helps coordinate the series in philosophy of physics. And finally, and most importantly, Patrick O'Hara and Katerina Randolph, whose generosity and commitment to intellectual engagement has made tonight's event possible. So can I ask for a round of applause for these? At the University of Washington seeks to engage with a broad range of contemporary issues of social, cultural, and political importance. We look for meaningful and innovative ways to apply traditional philosophical skills, most centrally those for analyzing and clarifying our reasoning. And we do so in order to grapple with fundamental questions that rest at the core of our lives, both as individuals and as members of society, who can influence and will necessarily be influenced by the institutions that surround us. Something that I think resonates with all of us the day after an election. Now, this sort of engagement requires us to reach out in the department and make connections. We have faculty who work with the University of Washington Center for Neurotechnology, the Medical School, the Evans School for Public Policy, College of the Environment, and departments including Jewish Studies, Classics, Germanics, History, Political Science, and even dance. We also reach outside the walls of our campus to facilitate conversations about politics in brew pubs, and to encourage Seattle elementary school children to ask questions in conversation with their peers in order to find their voices at a very early age. The O'Hara Lecture Series in Philosophy of Physics fits this mold by providing a forum for broad engagement with the remarkable achievements of contemporary science, many of which, I might say, are taking place on this campus. In particular, the series creates opportunities to grapple with the implications of fundamental physical theory, to enhance our understanding of the world we inhabit and our place in it. I want to thank Patrick O'Hara and Katerina Randolph for making these lectures possible and creating an opportunity for us to interact with our scientific colleagues here across campus and with people throughout the Seattle area interested in deeper understanding of contemporary science. I will also point out that the fourth lecture in this series will come in May of this year. And we hope you'll all be able to join us at that time as well. We're excited tonight to welcome Professor Nick Huggett, who is Liberal Arts and Sciences Distinguished Professor of Philosophy at the University of Illinois at Chicago, as the speaker for tonight's lecture. The general structure of the evening goes as follows. Professor Huggett will present his lecture in the first hour, followed by approximately 30 minutes of Q&A. Afterwards, you're all invited to a reception in the Walker Ames room, which is just across the hall, which will run from approximately 8:30 to 9:30. And we hope that will provide an opportunity for continued conversation and engagement with the issues that we're going to be talking about tonight. To help me introduce the speaker, I'll now turn the podium over to my colleague, Ben Feinzig, an assistant professor in our department, our own resident UW philosopher of physics, whose research focuses in particular on the implications of algebraic formulations of quantum field theories. Ben?
And let's just start by also thanking Andrea Woody, who has also played a role in organizing these lectures. So It's my pleasure to welcome Nick Huggett, our speaker for tonight's O'Hara Lecture in Philosophy of Physics. Nick is a liberal arts and sciences distinguished professor of philosophy at the University of Illinois at Chicago. Professor Huggett works primarily on the philosophy of quantum gravity, although he also has wide-ranging interests in the foundations of quantum field theory generally, and also the philosophy of space and time. His work strikes a careful balance, I think, between engagement with cutting-edge physics and also respect paid to our philosophical and historical predecessors. So in particular, Professor Huggett's research engages with details in theories of quantum gravity, especially string theory, as we'll hear about tonight. As exemplified by his, for example, by his edited collection, Physics Meets Philosophy at the Planck Scale. I find it impressive also to see how his work goes beyond contemporary physics and is informed by historical examples from both physics and philosophy, as demonstrated by his volume, Space from Zeno to Einstein, which I also teach out of. And Professor Huggett has also taken on the task of making accessible the significance of these philosophical questions, especially questions about the relationship between physics and philosophy in these fundamental areas. In his popular book, Everywhere and Every When, Adventures in Physics and Philosophy. He's currently working on a number of other books on quantum gravity. I opened up CV and noticed there are 5 books in progress. Is that right? How does he do it? But
2 of them are just editing. So
I see. So only 3 books. Now I'll also mention that Professor Huggett's work has been funded by a number of granting institutions, including the National Science Foundation and also the John Templeton Foundation. Most recently, he's been working on a John Templeton Foundation project titled Space and Time After Quantum Gravity. And it's some of the work from this project that he'll be discussing tonight. So without further ado, please join me in welcoming for this talk, Explaining Space-Time.
okay, is this him? Can you hear it? Is it amplified? It's on. It's good. Okay. Okay. Well, thanks very much for, let me just say, reiterate all the thanks that were given there as well. It's a really great honor to be here and a really exciting opportunity to talk to you all tonight about some of my work. So thank you. So I think I understand something about the composition of the audience. That there's a fairly general audience, there's some specialist philosophers, there's some physicists perhaps. I tried to give a talk that mostly addresses everybody and that everybody can follow. A few asides maybe to some of the specialists just to make sure we're on the same page. Okay. So the other note was, excuse me if I read from my notes from time to time. I think there's a lot of interesting things close to what we're going to talk about tonight, and I have a little habit of digressing too much if I don't really kind of keep focused on what I want to say. Survey the room about you. Okay, we observe the world, people, chairs, walls, screens, distributed in space and also in time. And put that way, it's natural to think of them, space and time, as some kind of arena in which events play out. Philosophers have long been intrigued by such an idea and investigated, the question of what to really make of the idea of an arena in this kind of context. These questions go back as far as philosophy. In the meantime, we've also learned a lot from science about these questions, from psychology about the nature of perception of space and time, and the focus here, we've learned from physics about the nature of space and the nature of time, and indeed, very surprising things about their nature. So, for a very short story, from the Newtonian conception of an absolute space, very fixed background with respect to which things play out, to Einstein's special and general relativistic theories. But even though Einstein's theories makes this space-time arena perspectival in a way, and dynamical, sort of interacting with matter, influenced by their contents, they still, at the deepest level, assume that this arena, space and time, is somehow part of the furniture of the world. Just very different from the way one might have naively thought it to be. So what I want to talk about tonight is speculative new physics of the last couple of decades, and more up to date, that in theories in which that space-time arena is not taken for granted as something that's presupposed, but rather something that has to be explained in more fundamental terms, explained maybe in the way tables and chairs are explained in terms of their atomic constituents, but maybe also explained, not just explained, but explained away in a way that we understand, say, a rainbow not to literally be a physical object. Those are sort of open questions here. And I want to sort of, I want to address the question of how that can be. Maybe it's worth just saying one quick clarification. These theories didn't arise because people thought, well, there's space and time, we need to explain them away in some sense, we need to understand them more fundamentally. These theories principally arose from the desire to find a quantum theory of gravity, to apply the ideas of quantum mechanics to those of general relativity. Numerous strategies have been attempted and have been applied to do that, and one striking feature that many of them have in common is various space-time structures and concepts fade away in these theories in one way or another. And that's what I want to explore today. And I hope... Good. So the specific question I have for you is this one. How can the ordinary space-time that we've just been talking about, this arena of experience, but we've understood more about it because of relativity, it also plays a role in quantum mechanics, how is it even possible in principle for it to be accounted for by a theory that just lacks spatio-temporal quantities or structures? I want to motivate that as a bit of a puzzle. I want to look at an example of how that might get done, and then come back to think about the general problems, the general conceptual problem that follows here. Okay, so just briefly I'll give you so you know what's coming. Here's the outline that I have in mind. Very briefly going to set up the questions that I'm interested in. And then we're going to work through, it didn't quite work properly, we're going to work through an example of it. The bulk of the talk will be introducing, you may be surprised to hear, string theory, actually explaining a little fragment of string theory to set up the issue that I'm interested in. Talk a bit about a symmetry that you find in string theory called T-duality that can lead you to think that indeed spatio-temporal quantities and structures are not fully present in string theory, and then follow how one might go about deriving position in particular as a spatio-temporal concept. And then at the end, we will return to the philosophical challenges, try and present the challenge and look historically, as Ben was saying, to what I think is a parallel situation in an earlier episode in science. Again, so we're going to develop a fragment of physics to sort of understand the issues and then apply some philosophical analysis to it. First of all, let's just frame those philosophical questions on a first pass, something that we will then return to later. So, in a paper a few years ago, my collaborator Chris Boutrick and I raised the question of the possibility of whether a theory which attempted to explain space could suffer from a problem called empirical incoherence, which is an idea from the philosopher Jeff Barrett. He raised this concept. And it's based on our argument, or the question we raised, is based on the thought that, okay, the evidence for a theory is always comes in the form of experiments or data collected in locally in space-time. Okay. The kind of evidence we have is by detecting a particle somewhere at some time, by images formed on the retina in a particular place, needles pointing to a certain reading. Well, just imagine a situation, which seems to be what we're talking about here, where such data led you to accept a theory which said, in fact, space-time was not real. That would be then to say that all those data that you thought you had collected, they weren't real because they are in space and time. And that would just undermine the theory, and so this would not be a theory that could ever be supported by evidence. It would automatically undermine its own evidence. So that seems like it might be an a priori argument that you could never believe such a theory. You never have good reasons, empirical reasons to believe such a theory. Well, if you think about it, there's probably a pretty straightforward let-out here. We drew a distinction between the real and the fundamental. What such a theory has to be saying is that space and time are fundamental ingredients. They're derived, but just as real for all that. Tables and chairs aren't part of the fundamental theory of physics, but we don't think that they're unreal, just not fundamental. Okay. So right. In the paper we discussed an article, or part of an article by the philosopher Tim Maudlin, who had made a similar point about a slightly different topic, but basically was saying the same thing here. So here's the idea as he puts it. One might try to derive a physical structure with the form of local beables from a basic ontology that does not postulate them. Beables is a technical term that you find in the philosophy of physics literature. It comes from the physicist John Bell. The idea of a beable is just something that's localized in space and time. We could talk about where this terminology comes from, but just think of it as something that's localized somewhere in space and time, an event or an object that can be somewhere or at some time. So he's talking about the same things as us. Okay, this derivation would allow the theory to make contact with evidence still at the level of local beables, but would also insist that at a fundamental level, the local structure is not itself primitive. But he went on to question whether that's the solution to that's the response to the empirical incoherence question. But Maudlin went on to question whether this strategy could really be carried out. But this approach turns critically on what such a derivation of something isomorphic to local structure would look like, where the derived structure deserves to be regarded as physically salient, so that's his term, rather than merely mathematically definable. Until we know how to identify physically serious derivative structure, it's not clear how to implement this strategy. Okay, I'm not going to say a lot about this challenge now because we're going to come back to it at the end. But you can think about what's being asked here this way for now. So suppose you found the theory of quantum gravity and it turned out not to involve space-time fundamentally, and yet you managed to derive a mathematical structure of space-time, and you found that that was empirically, agreed with experiment, agreed with observation. Would that really give you evidence to believe that the world was at bottom without space-time? Okay. All right. I think to really understand that question and to make any progress on it, we need to turn to our example. So, I'm going to teach you some string theory. And I think it can be done without any real heavy mathematics of any kind at all. At least the important conceptual idea that I want to share with you, I think. Okay. Very briefly, just to put string theory into context, just think about theories that go at the history of physics earlier. At the dawn of modern physics in the 17th century, Descartes had the idea that all physical processes had ultimately to come down to geometric chunks of matter in motion, and the only way they could interact was by contact action, literally banging into one another. Well, as we will talk about later, after the success of Newton, who I have here, and then later regarding gravity, and then Faraday and Maxwell regarding electromagnetism, people came to accept the idea of a field, that indeed objects could interact at a distance by producing, sourcing some field that actually extended out in space. So I've drawn here something like a potential field. You can imagine the large object is creating a field, which is like a curved potential, like a hill, and it affects the smaller object because this potential that it's the source of now makes the smaller object want to roll down towards it, converting that potential energy that it has higher into kinetic energy as it moves towards the heavier object. Okay. So the idea of a field as something extended in space, in particular in this case, accounting for the forces between objects that appear to be at a distance. Second step in this story is the quantum revolution. Planck and Einstein, in the first place, thinking about the electromagnetic field, came to understand that it was actually not continuous, but in a sense composed of chunks or quanta, in particular photons. And so, let me see if I can do this. That field that what I tried to represent here is that field that looked like it was smooth, in the quantum picture can in a sense be thought of as being built up of chunks of quanta, states of photons. Okay, which I represented here. A little later, the third picture on the bottom here is Dirac realized, thinking about electrons, that much the same story applied to particles and not just fields, not just force fields as well. So I bring this up because strings, to put them in historical context, can be thought of as a next step in this development, this way of thinking about physics, this kind of theory. And so we're going to start by thinking of a string as a one-dimensional filament in space. I think time aside for just a moment. And then there's two possibilities. If I give you a piece of string, either the ends aren't joined up and it's an open string, or you could think of the ends being joined up and actually have a spring which is going to represent a string. So if the ends aren't joined up, it's open, but I can't actually join these up, but you can join them together into a loop. And then what I pictured here is how a string would then look in space-time. I add a time dimension, so either have a line waving and propagating forwards through time, or in the other case, it's a wiggling tube, because I have it every time a closed string, a circle. Now, the first thing to know about the strings, or maybe this is the second thing, I've told you the first thing, is that it, like a spring, it has an internal tension, a huge internal tension. I was looking it up, and 10 to the 50 newtons is the Planck force. So an incredibly stiff spring, but still a spring, like a regular one, in that regard at least. What this means is, if it moves at all, it's going to start vibrating. That tension is going to cause it to wobble and stretch and unstretch. So, thinking about it that way, it seems you need two things to describe the state of a string. You need to specify its overall motion, and you need to, center of mass as it were, and you need to specify how it's vibrating. If you know the rate at which it's vibrating and how it's moving, it seems from that description you know everything about the string. Well, crucial for our story, there's one other thing that you need to know, but we'll come back to that in just a minute. All right, so I bought this spring at the hardware store because it really does exhibit and demonstrate how to think about a string really quite well. I mean, obviously there are some disanalogies, but it is something with an internal tension. I'm going to throw it up. The embarrassing bit is if about one time in 3 I drop it, and that doesn't look so impressive. But I'm going to throw it up, and what I want you to sort of focus on as it's moving, while I'm concentrating on catching it, is motion, but you'll also see that it's vibrating. Okay. It won't just go if I throw it hard enough. Alright, this is my bad luck time, so I won't try again, but I hope you can see as it goes. It's moving, it's vibrating. That's fine for thinking about how a string is. That's great. Okay, very good. And I really like to, bring that out because if there are, people who are physics undergraduates, people who've taken a little physics, you probably have, after very few classes, enough basic physics to think about how you would describe the motions for that string. The basic, starting from this point of view, the basic equations of motion, maybe the action or the Hamiltonian you write down for the string, really are just like the ones for the spring. I mean, it's relativistic, but basically it would be very familiar kinds of physics. You can probably think about how you would go about that. Okay. So the other thing you need to that's useful to know is string can vibrate in different ways, at different frequencies, with different pitches, as it were, and when you fundamental idea. An important idea in string theory is the strings are really small, so if you looked at them, as it were, with a microscope that didn't have enough power to really resolve them as an extended object, they would appear as particles, and one can show the basic idea in that story is the different modes of vibrations, the different frequencies, the different pitches of vibration would then appear as different kinds of particles, particularly particles of different masses. So that means strings have the capacity to understand the particles, the quanta of quantum field theory. That's the sense in which it's the third step in my story. The picture now looks like, we'll go both ways maybe. On the right here I have a field, one of those Newton, Faraday, Maxwell classical fields. From Einstein and Planck we have that it's really composed of quanta in a certain way. Going even fine, looking even in a more detailed way, we see each of those quantum, each quantum is itself a string in a particular mode of vibrations. So we have a strategy of building up the things we want to find in the world from strings to quanta to classical fields. And that's the sense in which strings are the next step in that story. And that's also then the sense in what we have here is all those fields that look like they were built of different quanta, when you look closer, turn out to just be made of strings in different states. So there's a powerful idea of unification here. Everything you want to get out of the observable world is just strings doing things in different ways. And the goal, the dream is that that includes gravity as well. Okay. Okay, so it is true that string theory has a way of explaining Einstein's theory of general relativity, the equations of motion for that, and since that involved Einstein's theory of general relativity really is a theory about the space-time metric in terms of which distances and times are specified, There is a sense already in which string theory derives space-time. But I want to look at an even deeper way. So, think about the closed string, the one on the right, and I want to talk about that extra variable in the description that I mentioned. In particular, I want to think about a closed string that lives in a cylindrical space. So, no time in this picture. I'm picturing two spatial dimensions. One that's closed, the circular one, and going up the page, one that's linear, that's not closed. And now think about it. If I have a closed string, there's something else I have to specify, namely how many times is it wrapped around the cylinder. So it might just be moving freely on the surface of the cylinder, but it could have been stretched around. So now it's wrapped once around, and that's what I have at the top. Or, I think in the bottom I have a single string that goes 3 times around the cylinder before the ends join up again. So this is an extra parameter that needs to be defined here. W we call the winding number, and that's just a specification of how many times the string is wound around the cylinder. To describe the so clearly, the more times it's wound around, the longer it is. The cylindrical space has some particular circumference, the distance all the way around. We'll actually talk about it in terms of its radius, which is just defined such that the circumference is 2 pi r. But this is a two-dimensional space that I pictured here, so there isn't literally any distance from one side to the other. There's just nothing there. The space is just the cylinder. There really is nothing inside. So this r is really just a sort of mathematical way of talking about the circumference. Okay. Then the basic, why do we need to talk about the winding number? Well, the more it's wound, the longer it is, and because of its internal tension, the more energy there must be in that string just from being stretched around the number of times that it is. Okay? So, and I will just go a little bit technical here, just to make sure that people who are thinking about the physics understand where I'm coming from. I'm going to say everything in words as well, but you can see the energy for the system is going to have 2 components. One that depends on the momentum p, and one that depends on the winding number. And of course, the larger the radius, the longer the string is when it's wound around, say once. If it's twice the radius, it's going to have to do twice the length. So the energy, as I say, is going to depend on 2 things. The kinetic energy, which goes like the momentum squared, and just the energy due to being stretched around the cylinder. And so that depends on how many times it's wound around, and the radius, the circumference. And it turns out that's a squared term as well. And again, some of you will know that specifying the energy, this function, the Hamiltonian, will also specify the dynamics for this system. We'll tell you the equations of motion for it. Okay, that formula is not, it's what makes what I'm about to say true, but understanding it's not crucial to what's coming up. Okay, so that's classical string theory. All right, so there's a note there about that. What we want to think, what we need to consider, and what string theory really is a quantum theory. So we need to understand the quantum version of this theory. We need to quantize what we have here, and this is going to change things in important ways. Okay, so I think quantization may sound a scary idea, but the one important thing that we need here, the fundamental idea that is, instead of specifying the position and momentum or velocity of an object, its state is just going to be described by giving a wave function, a function that lives in the space of the object. And from this, one can then derive statistical information about the position and momentum of the system, just using a standard algorithm. So, usually write psi. Instead of telling you where the thing is and how it's moving, I'm just going to give you a function over the space. And from that, you can extract physical information. And what you need to know about the wave function in this case in particular is the wave functions we're primarily interested in. The string lives on the cylinder, so they're going to wrap around this cylindrical space-time, this cylindrical space. And imagine it's just a periodic sine wave. So it's going to have, if it's a sine wave, it's going to have a certain number of complete cycles all the way as it goes around. So if I unwrap the cylinder in the picture, I go from one point in the cylinder all the way around back to where I started, 2 pi r further along. And for instance, the wave function might just complete one cycle, as it does in the bottom, for the n equals 1 case, or it might complete 2 cycles, as it does above, for the n equals 2 case, or 3, or 4, whatever it is. And so that number n is the wave number of the wave function, and it just tells you how many complete cycles the wave function has as it goes right around the cylinder. And then that determines by the quantum algorithm the momentum of the system. Indeed, this is the basic idea of the Bohr atom, and you may have heard of the de Broglie rules that identifies then the momentum with this wave number divided by the radius of the cylinder. Basically, this is relating it to the frequency as it goes around. Okay. Right. So what we're interested in is the momentum of the string, and that's just going to be given by this wave function, or in particular the wave number, how many complete cycles the wave function has around the cylinder. Okay. Well, that has to be a whole number, so that we've seen that momentum is quantized. It's got to come in some multiple of a whole number, some whole number multiple. N equals 1, 2, 3, whatever it is. So let's think about the winding number, that other parameter that we need to include into the theory. Well, we know that comes in whole numbers as well. It could be wound 0 times, 1 time, 2 times, 3 times. And so we see the very same representation is going to work here as well. We need a wave function wrapped around a cylinder, and the number of complete cycles of that wave function as it goes around the cylinder is just going to tell us how many times the string is wound around space. Just the same idea. The important point, though, is this has to be a second wave function. One wave function is telling us the momentum, the second wave function is telling us the winding. But moreover, this second wave function does not live in the same space as the strings. Does not live in the same space as the wave function that's telling us the momentum, because, well, you can look at the Hamiltonian and see why this is. It lives in a space that has 1 over the radius of the space we started with. Okay? So I'm going to draw a picture to sort of emphasize that again, but to give an argument from authority, a quotation from an article Ed Witten, one of the sort of founders and movers of string theory, said about this. He described this winding space as literally another direction, peculiar, like interpolated quantum string theory. I started with one cylindrical dimension, and what I found is, because of winding, I have to double count. There have to be 2. And you may have heard in string theory there are the tiny compactified dimensions that you can't see. These are, what I'm talking about now is in addition to that. Every one of those also has its second partner. Okay? So, what do we look like overall? This is sort of the full fragment of the theory. To describe the string, we need two wave functions living in two spaces, spaces that have reciprocal radii. So we started off by thinking the space the strings are living in, the one on the right, radius r, is our universe. It's very, very big. The visible universe is, here we go, something like 10 to the 27, 28 meters. Huge. Okay. What we've said is, well, to describe it, there has to be also another tiny space that has 1 over that radius. By the way, 1 means something like the Planck length. It's very, very small distance. I'm using units in which 1 is the Planck scale. So it's absolutely tiny, tiny, tiny. But it has to be there as well, this extra dimension that's dictated by string theory. Okay, and in each there's a wave function. I've got psi and phi that determine the momentum and the winding. And in particular, if they are just sine waves going around, the wave numbers are what determines the momentum and the winding. Okay? You just count the complete number of cycles. Okay. All right. Great. So now you know string theory. That's not a total joke, even. I mean, this actually gets to the fundamental sort of points that we need to see here. It is, in fact, kind of an approximation to an approximation of string theory, but it's capturing the important content that we need here. I hope the basic idea is then kind of clear enough about this toy fragment. Okay, keep that picture in mind, and you're going to see it appear in various guises as we go. Okay. You might now notice that one could produce a similar but different version of string theory in which space has radius 1 over r. What if we started off with 1 over r as the radius on the right? Because then the radius on the left, because then the radius on the right would be 1 over r, which is just r. So let's draw that picture. Here's the second theory we're working in this way. Okay. So it looks like I'm going to fill in some more details as we go, but looking at those spaces, it looks like the first version of string theory we started with, but with the radii reversed. Okay. So let's just think about this for a second. In the first theory, it's supposed to be a theory of strings that are moving around a space of radius r, some very big number. Strings are moving around the space on the left, winding around it, moving around it. That's what the theory is talking about. In the second theory, we have strings again, but they're moving and winding around a really small space. Again, the one on the left. Okay. So that's the fundamental difference between these two in the first place, is how big the space the strings are living in is. Okay, well, carrying on with this, developing this new theory, and in the same sort of spirit, you might think, well, what happens if I also exchange the two wave functions? So I've done that too. The wave function that was on the big space is on space is moved in the first theory, becomes a wave function on winding space in the second. And the same for the winding wave function. This has the same effect as just if these are, we're just counting cycles, they're just sine waves, exchanging the wave numbers between the two theories. And then it's a simple mathematical fact, this is the bit I didn't write before, that if you make this exchange, you leave the Hamiltonian, the energy invariant. So, okay, if you like to look at the equations, you can just see that that's a simple fact about what's going on here. But the cache value of this is both of these theories allow the same set of energies for the strings. So if I just told you what energies the string were possible in these two theories, what energies strings could have in these two theories, that wouldn't distinguish the two in any way. Okay. And this is a symmetry of the theory. It's called T-duality. Okay. All right, well that's kind of neat and maybe interesting, but starting to think about things that way, look, if I really wanted to tell which of these was the right theory, well, I'm not going to, obviously measuring the possible energies that I see is not going to help, but isn't there a much simpler way of doing it? I'm just going to measure how big the universe is, and then I'll know which one of these two it is correct. Clearly the universe is very big, and intuitively, clearly then it's theory 1 and theory 2 is just crazy. But I want to talk a bit about why that's way too fast, and in fact not the case. And I'm going to do it through an analysis of a paper by a pair of very good physicists who are very involved in cosmology and string theory, who gave a beautiful philosophical analysis of this situation. It's very interesting because this paper appeared in a hardcore physics journal. Nuclear physics, big. But we're going to talk through it and see physicists really applying a philosophical analysis to what's going on. Okay. Because T-duality is not just restricted to the energy spectrum, as we've seen it so far. It's a complete correspondence between the physical content of the two theories, between the values and evolution of all physical properties of the string. Okay? As they say, the symmetry is not just a symmetry of the spectrum, rather it is a symmetry of the whole string theory. Any physical process computed for the strings in a cylinder of size R is identical to a dual process computed for the strings in a cylinder of size 1 over R. All the scattering amplitudes for dual processes are equal. That just seems absurd, right? Again, we just look around, just survey the room. It's much bigger than the Planck length. So the universe is much bigger than the Planck length. We must be living in the in the large radius of theory. That would have to be the correct one. So, of course, one is at first sight tempted to disbelieve this duality. How is it possible that we cannot distinguish the small from the large? After all, the notion of size seems to be an invariant concept in general relativity. We can measure the size of space by measuring the time it takes to send a light ray from one side to the other. How could this possibly fail? So to analyze the situation, they do something that's really useful in this case, is to think about how to operationalize the situation, specify a particular physical measurement you would use to determine the size of the universe. And the simplest thing that you can think of is, well, send a light ray, a packet of photons around the universe. You know it's traveling at the speed of light. Time it. You can just simply do the calculation then to find out the size. And, all right, so I've drawn a picture of a photon going around and coming back. And we measure the time, and of course, if we did such an experiment, it would take a very, 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 very long time. Okay. So to make sense of, right, good. And let's see. All right. For dramatic effect, here's the photon going around. Universe is very big, takes a really long time. And if it's really small, it takes a really short time. Okay. Okay. So why would this not work? How could these things give out, in fact, the same answer? Okay. There's two parts to their answer in this analysis. So the first one is we need to talk about what the string theory and description of the apparatus is here, namely the light pulse. How would string theory actually describe that? When we see that, we can see what prediction is actually going to come out of the theories, the two different theories. Okay, well, the beam of light is an electromagnetic wave, some kind of electromagnetic pulse. As we saw, that's composed of photons, and in turn, the photons are states of strings of a particular kind of vibration. All right, so it's just a collection of photons of strings of the right kind, and so we can ask how the pulse would be composed. As they say then, the problem in the sort of initial reaction to the thought experiment is that it fails to take into account the quantum nature of light as well as the stringy nature of the winding modes. If the size of the box gets smaller and smaller, it becomes energetically more and more difficult to prepare a localized light signal that we send from one side to another. So the point is, by the scale of the theory, we have to make a super powerful light pulse, laser pulse, to send around the universe in this way. But by the scales of the theory, it uses very little energy. It's a very low energy state. So the question you have to ask of the two theories is, how do you create a low energy state that looks like the light pulse? In the first theory, with the large radius, huge universe, in fact, winding a string around even once would require a vast amount of energy. As I said, the tension is 10 to the 50 newtons, and the universe is 10 to the 27 meters. So it would be a vast amount of energy stored in the string if you tried to wind it around. So any energy you have to make the photons, this packet of light, has to just all be put into the momentum of the strings. Okay? And so that means we're not going to have any, in theory one, we're not going to have any winding state. It's all going to be a wave function that lives on the big space on the left, describing momentum. Okay? So there's no winding, so there's really no wave function in this particular case. But in the second theory, things are reversed. The shortest possible wavelength on the bottom row now is 1 over r, which is a tiny length and corresponds to a very short wavelength, so a huge amount of energy. But even more intuitively, now we're talking about a tiny, tiny cylinder, and so it takes hardly any energy at all to wind a string around it. Okay? So this very little energy that we have to make the light pulse is all going to now be put into winding energy. Okay? So the pulse, right. And as they say, on the other hand, the energy of winding strings decreases proportional to r, and it becomes easier and easier to create winding modes. It becomes easier to construct light signals using the superposition of winding nodes. Okay, just to make sort of the point, if I just have a little energy, in a big space I have to put it into momentum, in a little space I have to put it into winding. That's the way it's going to go. So the two theories are describing things differently. Okay? But now you think, okay, how exactly can that be? How could a collection of little strings wound around a very... sorry, before I do that, I have a picture to go with what I just said. Okay. In the big space I have momentum, in the little space I have winding. Okay, but looking at that picture, how could a bunch of strings wound all the way around a little space look anything like a pulse of light moving around a big space? After all, that's what the experiment is really, the result of the experiment is that there's a pulse that moves around something that appears to be a big space that takes a long time. Okay. And they ask exactly this question. How can such a state be localized in space, as the winding modes are highly non-local, since they wind around the whole space? The point is that the notion of position is a derived concept. Okay. Finally, we're getting to exactly to the point I wanted to get to in terms of this example. In ordinary quantum field, okay, so we need to sort of understand this idea, why position is a derived concept. Okay. This is the second step of that analysis. In ordinary quantum field theory, we define the position in terms of spatial wave functions. But because we're in string theory, we're not actually logically required to do that. We don't have to view space, the one in which the strings move and are wound around, as we don't have to identify that with the space of experience, ordinary space, the space of science. Because there's another space, this second winding space in the picture. There's nothing logically requiring us to identify ordinary space with string space. From a logical point of view, we could equally well identify it with winding space. String theory provides us with two dimensions, two directions, and either one is equally fit to be understood, at least in principle, as ordinary space, the space we're trying to understand, the arena that we're talking about. Okay. Right. That idea is the big kind of conceptual move here. So as they say, well, given that, we need to think of position as a derived concept. Okay. In string theory, we can instead, we don't have to define it in terms of the space in which the strings live. We can instead define position in terms of winding space wave functions. In one definition of position, the radius is r, and in the other, the radius is 1 over r. There is no physical principle which tells us which definition of position is more fundamental, and therefore they're equally valid. The philosophers may be feeling I'm accepting some of these things in a rather uncritical way, and I am, because of where I want to get to, and obviously there's lots we can sort of talk about here. Okay. Given this conceptual point, we really better stop calling this space on the left space, because that seems to refer to the ordinary space of experience and science, the one we just measured to be really big. What we mean on the one on the left is the one in which the strings live, the strings themselves move, the strings wind, and there is a standard name for this. That. That wasn't fun. I think I might have skipped through it. It doesn't matter. There is a standard name for this. It's called target space, or I'll call it T space. So just bear in mind we have three spaces in play here. String theory gives us target space in which the strings live and the momentum wave function lives. It gives us winding space in which the winding wave function lives. But remember, the winding wave function, the W space wave function, just tells me how many times the string is wrapped around T space. Strings don't literally wind around winding space. It's just a home for the wave function that tells me how many times the string is wound around target space. Okay, so we've got target space, winding space, and ordinary space, the one of experience. And the question here is, which of target and winding space is identified with ordinary space? And the point they've just made is it could be either. And in that sense, ordinary space is a derived concept. Okay. So now, putting together Brandenburger and Vathler's two steps, thinking about theory 2 here and how it would explain the long time it takes a pulse of light to go around space. Okay, if the radius of target space is small, as it is in the bottom of this picture, and then that of winding space is large, it's 1 over r. So first, we identify the light pulse with strings wound around the small target space, which then is described by a wave function that's local in the large winding space. So there's some state of strings wrapped around the little 1 over r space, but the wave function for that lives in the large winding space, and I've drawn it now as a wave function that's localized somewhere there. It's not just a sine wave, it's some local packet that's that lives in winding space. Okay. Second, we use our freedom to identify winding space with ordinary space. so that the position of the pulse is now identified with the position of the wave function in winding space. Thinking of a wave function that's zero most places, but is non-zero in some part of winding space. And that is now identified with the light pulse. It's identified with a localized wave function in winding space. And of course, going to the top of the picture, in the large radius jewel, everything is reversed. But the light pulse is identified with a wave packet, a localized wave packet that lives in the large T-space. In this case, I'm going to do the obvious thing and identify T-space with ordinary space. Either way, I have a large space with a wave packet identified as the light pulse, but the two theories say different things about what that space is. One says it's T-space, one says it's winding space. Okay, and so finally the light pulse is guaranteed to take a long time. Both jewels describe it with a localized wave function traveling around a large radius space. They just disagree whether it's T or W space. Okay. That's the difference, one of which one they count as ordinary space. But in either case, we just have a wave packet that moves around the large space, and that is how we derive the motion of the light pulse around observed ordinary space. As Brandenburger and Baffer say, no experiment tells us whether we live in a universe of size 10 to the 62 Planck lengths, 10 to the 10 years, or in a tiny universe of size 10 to the minus 62 Planck units. Of course, the more useful definition is in terms of less energetic states. With this definition of position, we see that the effective minimum size of the box is r equals 1, the string length. Okay? But to come back to the main point here, let us emphasize one important lesson that we have learned. The invariant notions of general relativity, such as distance, may not be invariant notions for string theory on short distance scales. So what we've just seen is that the size of the universe is derived. It has a definite value for ordinary space, but not for target space. There's two possible values that it could have, because the jewels disagree. And not just distance was derived in this way, we had to also derive the notion of position, the awareness of, where was that pulse? That's also something that's derived, according to them, in this theory. Okay. One theory says it's localized in, one of the jewels says it's localized in target space, the other says it's not, it's instead localized in winding space. Okay, so that's the derivation. And I realize I've gone a little bit longer than I said. I will go rapidly through some things, but try to wrap it up. Okay, I apologize for that. Bear that in mind, I want to come back to the philosophical challenge that we saw from Maudlin. Okay. As he said, one might take a theory and from it derive local variables, local space-time structure and quantities, even if they weren't present at the fundamental level. And the string theory example is supposed to be, to some extent, an example of that. And you may feel it's not this, it's derived in, the position and distance are derived in the sense that Brandenburger and Baffer explain, but string theory does bring a lot of spatial-like structure. I mean, we have winding space, we have target space, they look like spaces. So this is perhaps not the most dramatic example of deriving position, deriving spatial structures. So I won't go into details now. If somebody wants to ask, there are more dramatic examples of theories in which you start with a space, for instance, here, which is not a space, but the fields don't live in space, but they live in the space of symmetries or transformations of the space, which typically has a different dimension than the space. Another possibility is we're used to x, if I multiply x times y, I get the area. And it doesn't matter if I multiply x by y or y by x, whatever order I do the multiplication, I get an unequivocal area out of it. Well, there are geometries where that's not true. So in a sense, there's no such thing as an unequivocal area. And these are theories from which you can derive, that start off with something that has even less space-time structure than string theory, and yet you can still derive space-time structures. And again, dualities are often taken to point to actually a deeper version of string theory, from which the target space and winding space themselves are derived from something even less spatial. So there are other kind of examples out there. They're more complicated than the one we've talked about, which is why I didn't talk about that. But let's just refer to Maudlin's challenge again here. Right? Deriving space-time as a way of... this approach turns critically on what such a derivation of something isomorphic to local structure would look like, where the derived structure deserves to be regarded as physically salient rather than merely mathematically definable. Until we know how to identify a physically serious derivative structure, it is not clear how to implement this strategy. So the key idea here is the question of whether a mathematical derivation of the kind we just saw is nothing more than that. It just shows a mathematical correspondence. How could we be further convinced that the theory was true, that we actually had an explanation of space-time, or of space in terms of something more fundamental? This is what Maudlin is getting at when he puts the question, he sort of is asking, how could we know that the spatial structure that we've derived is physically salient? So look, one might always ask this question about any theory that derives predictions from an unobservable structure, but I think Maudlin sees a special worry in the case of deriving space, because our grasp of when a derivation is salient, the grasp we have now, depends on space. So for instance, the atomic account of this table makes this table physically salient within the atomic theory because the atoms are located, for instance, where the table is, and that they have the collective causal properties of the table. And these are inherently spatial notions. So to say now, because our theories are spatiotemporal now, when we think we have a spatiotemporal derivation, we appeal to spatiotemporal criteria to show that. But that means when space and time are absent, we're just going to be lost in doing this. We just won't be able to know how to distinguish mathematics from explanation. Okay. I spent too much time at some point of this talk, so I'm going to actually just skip over my historical example. If somebody wants to ask me any questions, I'm happy to come back to it. I wanted to talk about an example to do with how people overcame the Cartesian idea that all action was contact action, which I think is there was a similar principle that a derivation was only physically salient if it appealed only to contact action, and this was a problem for the interpretation of Newtonian gravitational action at a distance. But indeed it was overcome by the empirical success of Newtonian gravity. People just gave up that as a criterion of physical salience and figured out what new criteria were. And the general lesson here is one of the things you learn when you learn a new theory is how to make good explanations, which explanations are allowed. And the optimistic message then is supposed to be, well, that's going to happen here too. We will figure it out. Okay, so I apologize for going over a bit. So I'm going to bring it to the conclusion. Because I want to use our example to sort of talk through this as a response to Maudlin, as an example of how we might develop kind of new criteria. How criteria of physical salience might come into this. Okay, so just to sort of review where we got to. So our Toys string theory does not take space-time as fundamental, but explains it as a phenomenon. Distance and locality are derived. That's the upshot of the Brandenburger and Vafa argument and the analysis that we looked at. Okay, plenty to talk about there, I agree. Okay, as I said, well, granted, there's a lot of spatial structure built into this. Two spaces, string spaces example, it's not the most radical way you might imagine space-time being absent and being derived. I mentioned some other examples. But that said, the example is enough to see how one would respond to Maudlin in this particular case. That's why I am interested in this example here, just as an example of how it could be done, and how one could demonstrate or come to a new understanding of physical salience, in this case, as a model for how it would play out in the other kinds of cases that I've mentioned. Okay. So first of all, so the primitive degrees of freedom are wave functions in a pair of spaces. We have target space and winding space. We don't just have them living in space in a trivial way. So that's the sense in which the theory is not spatiotemporal fundamentally. We saw how to derive motions of wave packets in those spaces in these theories, identifying light pulses. Let's just do this. Okay. So there's a formal derivation that identifies wave packets moving in a large space. But more than that, these wave packets of lower energy are identified with observable particles, the Beerballs that Maudlin is referring to, in particular photons making up a localized pulse of light, things with which we can measure space. What we have here is exactly a postulate concerning physically serious derivative structure. There is a wave packet in the theory that's the wave packet I drew moving around target space or winding space is mathematically in isomorphic correspondence to the light pulse. But what we postulate further is that that's exactly right. It isn't just a mathematical correspondence. That is how the light pulse is represented in the theory. That's what the light pulse that we observe corresponds to in stringy terms. That is physically serious derivative structure. And then on that basis, we don't have to assume that target space is ordinary space, but now it follows that ordinary space is going to appear large, an interaction local, whether target space is taken to be big or small. Because in a small radius, if target space has a small radius, this identification is going to tell us to look at winding space, which is big. That's where the physically serious derivative structure lives. And so that actually amounts to a physically salient derivation of space-time structure. It actually does, this new postulate is really what's doing the work of telling us how we should actually go about explanations in this theory. Okay. And then the idea is, if you looked at other theories, you would find a similar story. This is part of the work that I've done thinking about these theories, is looking at exactly the point where you have to make a postulate about which mathematical structure you're going to identify with observable structures, which ones you're going to count as physically salient. And these have to be new postulates because you don't have a space-time structure to appeal to make it happen. But it is something you do in the derivations. Okay, and well, thank you. That's the talk, and there were some references in there that I wanted to I'll put up for you. But thank you. That's all I have.
So we have some time for have some time for questions, and I will try to keep track of them for Professor Huggett. So if we can see hands, and if anyone's too far in the back, then we may try to work with the local mic. I can see one.
I'm glad you asked that. Let me just...
So the question was to hear a little bit about the historical example.
Yeah, I just wanted to, as I said, give an example where it seems that Magdalen's challenge played out and was addressed in an earlier historical context. So as I said, in the 17th century, at the origins of modern physics, Descartes had this idea that to give a proper physical explanation, we need to talk about the shapes, arrangements, motions of objects, and the only way they can interact is through contact action. So this led him to a theory of gravity, which is I put on the right, in which he thought of the motions of the planets as caused by a very fine fluid orbiting like a vortex around the sun, carrying the planets with it. And in fact, this is a picture from the Principles of Philosophy, and S here is our sun. This cell, so the whole picture shows a section of the universe. Each cell is a solar system, and you see these lines rotating around with a vortex circling around the sun, and it carries the planets with it, and that's why the planets orbit the sun. The picture's kind of neat because you can see there's other cells, they're sort of stacked like ball bearings, they don't all turn the same way. This is a cell that's sort of orbiting out of the page. The vortex is coming out of the page and around. Some of the vortices do have suns in the middle, some don't. This line here, I don't know if you can guess what it is, but this is the Cartesian theory of what a comet is. As it's moving, it's not in orbit around the sun, but it's carried from vortex to vortex through the different cells. Okay, so you had this whole qualitative picture that's based on the idea of contact action. And how could the planets be moving? There has to be something there pushing them around, and it's this vortex that's pushing them. And I contrast that with the picture on the right. This is Newton's death mask. And this is from Proposition 1 of the Principia, which is starting the derivation of universal gravitation. S again is the sun, and A, B, C, D, E, F. This is what he's thinking about is a little arc of the motion of a planet in its orbit. And what's happening is, well, in this case, it's being periodically pulled towards the sun. So I put this up to, there's no contact action going on here. It's sort of action directed towards the sun. That's the more mathematically successful theory. But, of course, Newton was famously sort of cagey about exactly what the cause of gravity was and how to think about it, whether it was an action at a distance or whether there was some mechanical explanation. But the Cartesians, and this idea of contact action was a very strong principle held by many physicists at the time. They were happy with the mathematical treatment that Newton gave, and say the mathematical, you give the 1 over r squared law of gravity, and from that you can demonstrate the motions of the planets. The Cartesians totally happy with that as a mathematical correspondence and a mathematical system for talking about gravity, at least within the solar system. But no way buying into it as anything more than that, because it seemed to clearly violate the contact action principle, the mechanical principle. Okay. And I have a quotation from Leibniz that I think makes exactly this point that he said to talking to Descartes. If God would cause a body to move around a fixed center without any created thing acting upon it, so let's think about a planet around the sun, it cannot be explained by the nature of bodies. For a free body does naturally recede from a curve in the tangent. Right? This carries on in inertial motion. And therefore the attraction of bodies is a miraculous thing, since it cannot be explained by the nature of bodies. He's just assuming, right, the mechanical principle, contact action. If the planets were really moving in this way without being pushed by the planet, it would just have to be God pushing them around. It wouldn't be natural science, it would be a miracle. It's just not physically salient. But as I said, the empirical success of Newton led to people come to accept the explanations in terms of action at a distance, although, importantly, that's not the end of the story either. We go from a story of contact action to a theory of action at a distance, but part of what Maxwell and Faraday brought, sort of introduced with their concept of the field is that actually, well, there's a different sense of locality that affects propagate at finite speed through a field. So it's not that things literally reach out and in an unmediated way cause distant effects. Okay? So the field concept of locality then replaced the kind of Newtonian action at a distance. But then we have quantum mechanics, and now we have a different kind of action at a distance. So what is kind of thought of as possible, what explanations are physically salient, what counts as a legitimate explanation, changes over time, depending on what the theory is like. And it's that sort of historical contingency that I'm suggesting will work in the quantum gravity case as well. If you have to derive space-time from a non-spatiotemporal theory, we don't know what a good way of explaining it is at this point, but that's one of the things, like in these cases, we'll have to learn from the theory. So, thank you for asking.
In the back?
Yeah, so in classical physics, we're familiar with configuration space and phase space, but still having an intuition that ordinary space is more fundamental and that these other spaces that we work in are just derivative. I'm wondering why not think something similarly about W space, the winding space, or the space of string theory.
Do you have a suggestion of how to think about it as derivative? Or?
I guess I don't understand enough to know why I wouldn't
Okay.
go that way.
So it's not quite like, so configuration space, you can sort of see how to construct it from the ordinary space, right? So the configuration space, if I have three-dimensional space and I have n particles in it, I can construct a bigger space that has three n dimensions, and then instead of saying where each of the particles is individually located in 3 dimensions, I just pick one point in the 3n dimensional space, and that tells me the information. But that's kind of obviously a construction. Okay, maybe this is controversial, but there's a sense in which it's obviously a construction from the n particles and the 3 space that I started with. I don't see any parallel way in which winding space is just a construction from something that's happening from the other space. I'm not saying it's kind of impossible to do that, and as I think I sort of said, I'm just going with, in this case, with the interpretation, the gloss that they're putting on things, because I want to get to this point about how to explain things. So, explain things when you have a theory that's not spatiotemporal. But I do kind of agree there are different kinds of interpretations that one might put on what's happening in string theory and the meaning of T-space and winding space from the one they do that you could consider. But I don't think it's quite as trivial as the construction of configuration space. That's helpful. And again, in general, I'll sort of refer you to some of the other types of theory where it's really clear you don't have something like an ordinary space.
Next question. We're all the way, well, let's see. Over here and then in the middle of the room. So we'll see if we can get the mic to you.
Okay, so as I understood it, when you have the duality between the T space and the W space, like the low energy particles live in the big space, so we can say that that's the real space. But I'm just a little curious about what happens if your spaces are more or less the same size. Like if your radius is close to 1, then what happens in that case?
Right. Can I just want to say one thing back again. So just because it's not that this is dual to this, but the duality is going up the page, not across the page.
Right, yeah.
Okay, so it's not that the T space is dual to the W space in one theory, but that, okay, good. No, so that's pretty interesting, right? So, I can't remember if I actually put the passage in there from Brandenburg and Raffer. I think it is in there, but I just went over it kind of quickly. Given that rule about how it's always, because of you have low energy probes, you're always going to see the bigger of the two spaces. Now you're imagining sort of dynamically, well, what happens if I start with a big target space and it gets smaller and smaller? Of course, what's going to happen at the point where it has radius 1, string length, and the two spaces are the same, if it keeps getting smaller, now your observable physics is swapping from from target space to winding space. And so what you actually see in that case is, of course, the universe getting bigger again. So you're tracking target space as it's getting smaller until it reaches the string scale. It keeps getting smaller, but as it keeps getting smaller, now winding space is getting bigger. And so that's what you're going to sort of see. So you see this kind of bounce. Does that make sense? Right? Well, look, this is big, this is small, right? This is like 1 here. This is the biggest space, so I see this one. But you tell me it's getting smaller, so I see it getting, my measurements, my photons take less and less time to go around it until it gets to size 1. Okay. At that point, all this time the winding space has been tiny, has been getting bigger. Now as target space gets smaller than 1, winding space starts getting bigger than 1. That's where the low energy is. The target space is getting smaller, so winding space is getting bigger. And that's what I'm observing by this analysis. So I think the passage was here, sort of, the string length is the smallest space can be, at least observable space. Okay, there's some interesting mathematics there. In fact, T-duality, if you know anything about this, is actually a gauge symmetry at this point, and there's actually some, right around that string length point, there is actually sort of some non-trivial physics as well. But I think thinking of it as a minimum length is sort of the key, sort of interesting conceptual thing to have here. Okay?
So I guess that the strings are constructed to behave like the particles. And so these two spaces, the T space and the W space, are then derived from that physical requirement, or that physical constraint. So when you say that the distance is then derived from these spaces, or from the theory, is that really the way that it's going, or is it that the distance is inherent in the construction of the string itself, so that it matches the empirical evidence?
I'm not quite sure I understand the construction of the strings part.
I don't know about this.
Yeah.
I'm making a big jump, but ultimately it has to agree with the results of our experiments.
Right.
So when you build the math that defines the strings, it has to match so that those vibrations correspond to real particle observations.
Right. So maybe there's two kinds of sense of construction that are going on here. Right? I mean, that's not how the atomic theory is built, but one has to, if it's right, the atomic theory has to be able to reproduce the table or, solidity. But I wouldn't say on that basis that, atoms are then constructed from tables.
But the math that describes the string is constructed so that it matches, so that the results match the observations.
Yeah, but in the same way that the math that describes the atoms is sort of constructed so that it reproduces the solidity of the tables. I mean, that's not a historical statement. So I didn't mean this, so you can think of the strings as not, that's a desirable property of the strings, of string theory, that it actually tells geometric facts and recovers space-time. But I don't think you have to sort of think about it that way. That's a sort of more fundamental story of how the world is, in the same way that the atomic theory is a more fundamental story about how the world is. And so then things are derived from it. Of course, that's what we wanted to happen. But the strings aren't sort of constructed from particles. The theory is developed, and you see it gives you this framework for understanding what the particles, say, really are in a more fundamental way. Does that help? No. Yeah.
So I think we are at the end of our designated time. So what I would like to do is thank our speaker and then invite you all over for a reception. And if anyone else still has a burning question, you know where to find me. Thank you.